Today we're digging into something that literally holds our world together, ladder cable trays. You'd think figuring out how far apart to put the supports would be pretty straightforward, right? Well, as we're about to find out, there's some hidden physics at play that can turn a tiny mistake into a massive failure. So let me ask you this. What happens when a seemingly small 20% error in an engineering calculation doesn't just cause a small problem, but spirals into a complete system failure? It sounds like an exaggeration, but trust me, it's a very real and very expensive possibility. And this isn't just theory. Take a look at this real-world example from a petrochemical project in Ningbo. They had a cable tray loaded up with a hefty 120 kilograms per meter. Someone miscalculated the support spacing by just 20%, a tiny oversight, you might think. But that one error caused the whole setup to fail its safety inspection. The result? They had to go back and completely rework 14 different support positions. Ouch. So yeah, that brings us right into our first part. How on earth did a small 20% mistake lead to such a huge headache? Well, the failure wasn't just some judgment call. It violated a specific international safety standard, IEC 61537 to be exact. This standard has a really clear rule about how much a tray is allowed to sag or deflect. It's called the L/200 criterion. If you fail that test, it's not a suggestion. It means your structure is officially unstable and unsafe. End of story. So how did they get it so wrong? This is where the physics gets, well, kind of mind-bending. I like to call it the fourth power surprise. Okay, so let's set up a common scenario. Imagine you decide to double the distance between your supports, maybe to save on materials. You go from 1.5 meters to 3.0 meters. Simple enough, right? It's just a 2 times increase. So it seems logical to assume that the sag right in the middle of that span would also just double, right? Nope, not even close. This is the part that blows people's minds. Doubling the distance doesn't double the sag. It multiplies it by a shocking 16 times. Not 2, not 4, 16. And here's the kicker. The reason why? The sag doesn't just scale in a straight line with the length of the span. It scales to the fourth power of the length. That little L in the formula is an absolute monster. It means any small change you make in distance has this huge exponential impact on how much the tray bends. This is that fourth power relationship, and it's what catches so many people out. All right, so if that force is so incredibly powerful, how do you fight back? What can engineers actually do to get a handle on this crazy exponential bend? Well, your first line of defense is the tray's design itself. That bending force goes up with the square of the span, but you can counter it by just making the tray stronger. Get this, by just doubling the depth of the side rail. Going from 75 to 150 millimeters, you make it so much more rigid that you can actually extend your support distances and cut the number of anchors you need by almost half. That's a huge saving. The other big tool in your toolbox is what the tray is made of. The material matters a lot. Steel is super stiff. Its elastic modulus is around 200 gigapascals. Aluminum, on the other hand, is way more flexible, at around 69 GPa. So what does that mean in the real world? It means for the exact same load and span, the aluminum tray is going to sag about 3 times more than the steel one. But, all these perfect physics calculations are one thing. The real world is a lot messier. It loves to throw a wrench in the works with factors that can totally ruin a good design. Let's call them the real-world span killers. You've got to watch out for these, because any one of them can slash your safe support distance by 15 to 30%. On a project in Shandong, for example, engineers had to add more supports on the outdoor sections just because the heat from the sun caused thermal expansion, adding extra stress. Then you have fittings like elbows and T's. They create weak points. And of course, if you're building in an earthquake zone, well, that changes everything. Which really brings us all home to our final and maybe most important point. You have to design, not just for what you need today, but for what you'll need tomorrow. Look, the best practice in the industry is to never, ever design a cable tray to 100% of its rated capacity. You always aim for about 70 to 80%. That extra 25% isn't wasted space. That's your safety margin. And just as important, it's your built-in room to grow. It means you can add more cables down the line without having to tear everything out and start over. So that really leaves us with this one big question to think about. And it goes way beyond just cable trays. When you look at any system being built, you have to ask, is this thing just built to solve today's problem? Or is it truly built to handle the challenges of tomorrow?